Hello and welcome back. Today we're going to be moving on to section 4.4. So this section is going to be a little different than the previous sections we had. It's actually going to be using derivatives to find limits. So in a way, how can we use our chapter 3 knowledge of here's a function, take its derivative, to find limits that are a little bit more difficult? So just a review with limits, you have indeterminate forms. And there are several types of indeterminate forms. Some examples are the limit as x approaches infinity, x minus 1 over x squared plus 1. So you can't really think of plugging in infinity. But if you want to think in that sort of sense, what you get by this plugging in is infinity over infinity, which is an indeterminate form. Another example is the limit as x goes to 1 of x minus 1 over x squared minus 1. If you plug in 1, you get 1 minus 1 is 0 over 1 squared minus 1 is 0. So that's two examples of indeterminate forms. Are these infinity over infinity, 0 over 0? Other examples that you might get, 0 times infinity, infinity minus infinity, 1 to the infinity power, and 0 to the 0 power. Now this section is going to be all about indeterminate forms and limits. Now the two most important ones in these sections are going to be these two indeterminate forms, the ones that look like fractions, the infinity over infinity and 0 over 0. Now note that what is not an indeterminate form is, sorry about that, infinity over 0 and 0 over infinity. This one's infinity and this one's 0. Another caveat with these indeterminate forms is you can also do similar things with negative infinity and get also indeterminate forms. And those might pop up in some examples, but right now we're just going to state it in terms of just infinity. Okay, so the thing we have to deal with this is called L'Hopital's rule. A little history about it. It was named after French mathematician Guillaume de L'Hopital, where if you're to spell it properly, you put this little caret on top. if I can draw one. Put a little caret on top of the O. He first introduced it in 1694 with Johann Bernoulli, because back in those days, you could pay someone to publish your work in their book, and it was published in the first book on differential calculus. Okay, so what does L'Hopital's rule say? Well, suppose you have two functions, f and g, that are differentiable with its second derivative, with its first derivative not being equal to 0, on an open interval containing the number a. And then suppose that the limit as x goes to a of f of x over g of x gives the indeterminate form zero over zero or infinity over infinity. Then what you get is that the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x. Provided the limit exists. So, really, you can just take the derivative of top, take the derivative of bottom, and divide by them, given these conditions, that you have 0 over 0 or infinity over infinity. This does not work for the other forms that we had. So you have to be very careful that you have either this form or this form. Okay, so let's do a couple examples and one non-example. So here's just a straightforward example that we can actually use our methods from chapter 2 to verify that this works. X going to 3 of x minus 3 over x squared minus 9. If you just plug in 3, you get 0 over 0. So we could do this two ways. If I start, I'll put it on the right, doing it by L'Hopital's rule. So I have this, and then equals 0 over 0. So then I'll say equals the limit as x goes to 3 of the derivative of the top is 1 over the derivative of the bottom is 2x by, I'll just abbreviate, L apostrophe H. And that's how I'm going to want you to do it on any of, quizzes, tests, is to state what the indeterminate form is and then put by L'Hopital. And so now we can just straight plug in and it's 1 over 6. Okay. Now if we would do algebra here and do just our methods from chapter 2, what do we get? Well, we have the limit as x goes to 3 of x minus 3 over x squared minus 9, which factors, the denominator factors into x minus 3 over x plus 3, x minus 3, and you get these two cancel, giving you limit as x goes to 3 of 1 over x plus 3, which is 1/6. So it does seem to work out, at least in this example, and L'Hopital's rules say those two will always coincide, that if you can solve it by algebra and it's in an indeterminate form, or you solve it by L'Hopital's rule, it doesn't matter, they'll be the same. Now, a little caveat with using L'Hopital's rule is don't forget your quotient rule when taking actual derivatives. The derivative of top over derivative of bottom is specifically reserved for L'Hopital's rule. It is not for the derivative of any function. Okay, another example is going to be, well, let's take a limit as x goes to infinity, natural log of x over square root of x. We're going to use L'Hopital's rule here. There's not really algebra I can do. This indeterminate form, well, natural log of x goes to infinity, and square root of x goes to infinity. We have the right indeterminate form. So by L'Hopital's rule, you get 1 over x over 1 over 2 square root of x. And this is a fraction that I can simplify a little bit. 1 over x times 2 root x over 1. Or what do I have? 2 over square root of x. And if you plug this in here, it's going to be 2 over infinity or 0. Because remember, any positive number over infinity or any negative number over infinity, you're going to just get 0. Okay. So now for a non-example on why you have to be careful that you have the indeterminate form. So this is a non-example. If we take the limit as x goes to pi from the left of sine x over 1 minus cosine x. If I just don't look at the indeterminate form and apply L'Hopital's rule, the derivative of sine is cosine, and the derivative of 1 minus cosine is sine, because you have that negative out front. And then if I plug this in, Cosine of pi is -1. Sine of pi is 0. Gives me infinity. But if I take the original one and evaluate it, instead of just jumping the gun here, what do I get? Well, it's going to be sine of pi is 0 over 1 minus -1, which is 1 over 2 or 0. So this non-example shows that you need that indeterminate form, that 0 over 0 or infinity over infinity, to actually use L'Hopital's rule. Okay, so there are other indeterminate forms. So between the one that we're going to go over today and the other ones that we'll go over in the lecture tomorrow, we will go over how to use this method of L'Hopital's rule to evaluate ones that have different limits of different indeterminate form types. So the one we'll do today is 0 times infinity. What does this look like? Well, the example we're going to do is the limit as x goes to infinity of x sine pi over x. Remember, sine of 0 is going to be 0. So pi over x goes to 0 as x goes to infinity. So this indeterminate form will be infinity times 0. Okay. So we need to think how, I can't apply L'Hopital's rule yet, but how can I make this, turn this into a form where it will work out? So what I'm going to do is I'm going to take this term and I know that this is going to be the same as 1 over x. Because, you know, the whole multiplying by the reciprocal, if you have a complex fraction, will give you that that's what x is equal to. Well, now what happens when you take the limit as x goes to infinity? Well, this top term will still give you 0, and then the bottom term, 1 over x, also gives you 0. So now we have what we want, the 0 over 0. So we could say that this is equal to limit as x goes to infinity. Derivative of sine is, well, we're going to have to use chain rule, cosine pi over x times the derivative of the inside pi over x is going to be a negative pi over x squared all over, well, this is going to be negative 1 over x squared. And that's by using L'Hopital's rule. Okay. Let's clean this up a little bit. You could factor out negative 1 over x squared to both the top and bottom. And these cancel, giving you the limit as x goes to infinity of pi cosine pi over x. Remember, limit as x goes to infinity of pi over x is just 0. Cosine of 0 is 1. So you get that this limit is equal to pi. So it does work out in this case that we can somehow change what this looks like to get the indeterminate form we want. And then we'll continue with more examples on this tomorrow and finish up this section. But remember, the other forms we still need to talk about are going to be, you still have that infinity minus infinity type terms. And then you also get the ones that are 0 to the 0, infinity to the 0, and 1 to the infinity. So this is the one type, this is the other type. And we'll finish that up tomorrow. Again, any questions, leave comments in this video or message me on Canvas.